Okay, so now we will start the parallel panel discussion. And here we will have a nuclear safety panel discussion with the facilitator is Professor Ming Li from National Tsinghua University. Please, Professor Li.
Sorry about the delay. Well, I Professor Ye's connection. Okay, so today we have three sessions on nuclear. First, we review the three accidents of nuclear power plant, which is Three Mile Island and Chernobyl and then Fukushima. Then we talk about the advance of nuclear technology. Okay, how can we keep the reactor nuclear power plant safer? The last session, we're talking about the future of nuclear power. We even have we even have some talk about the fusion reactors. Now in the panel discussion, we have three new people joining us. One is Dr. Rich Moore from UK, and the other is Professor Cho from Korea, then Dr. Liao from Taiwan. And because we are running kind of a little bit late, so I won't introduce them. So for those people who did not give a presentation in the formal session, they will have 5 minutes to talk about their point of view about the nuclear power. So shall we starting from Professor Rich Moore, Cashmore?
Okay, if I may begin. I'm going to repeat a few things that you've heard about today, but I want to emphasize I come at this from the background of facing up to the biggest challenge of the 21st century, which is getting down to a global zero carbon emissions by 2050. And for me, that means we have to have important and we have to have safe nuclear electricity. Reminding you of some of the COP21 conclusions, which I want to carry forward a little bit. Really, we now know that the temperature rise, the global warming is going to depends on the total CO2 emitted. Therefore, we've got to use all our possible tools available to reduce CO2 emissions. And the next point I want to make is that to be able to do it by 2050, we've got to act very, very quickly now, because 2050 is not very long away, and I don't think we've been emphasizing that enough. Also, some of the conclusions of COP21 will, subsequently, we need different solutions for different locations in the world. Everywhere is somewhat different. And particularly between developed and developing nations, there's no global optimum solution, it will vary. But there's a burden then on the developed nations that are going to develop some of the techniques to do this, and particularly nuclear. Then we've got to make things that are viable for people elsewhere in the world. We've got to be able to export the solutions, because everywhere in the world has got to get to net zero by 2050. Consequences are, we've got to reduce energy demand. We've heard about that. We've just got to get rid of fossil fuels, and we've got to substitute with them genuine, viable alternatives that don't lead to CO2. That means the renewables that we've talked about. It means nuclear, and we've heard that persuasively put in earlier talks. But I do believe in the end, we will have to use some fossil fuels with carbon capture and storage. So we've really got to use every tool that there is in our hands. Now, here's a little introduction about from the UK, where I come from, about the energy usage in 2017. And look to the left-hand side of this picture, because it emphasizes just the scale of the problem that we've got to deal with. Because in that left-hand side, you see basically all the energy usage in the power, heat, and transport categories. And you see the green there representing what's already, shall we say, green. We are a long, long way off being able to get down to a completely green system. And particularly transport and particularly heat have hardly begun any of the activity at all. So that's the real big challenge in the next 25 to 30 years, is to change that into all green. Now, there's a problem associated with that, is we don't know how to do it, in fact, to complete that exercise. But what we do know in transport, we have electric vehicles. Electricity is going to be important there, but we also know there's probably got to be hydrogen or ammonia or some other source of power for the transport. On heat, we haven't got to a solution either for heating all of the homes and buildings in the world. We do know that electricity is important there, but we have to come up with some other things as well to be able to do that. And of course, in industry, again, they're very big users of energy. And again, we can use electricity there, but you've still got to find ways of getting to even higher temperatures that we don't know how to do at the moment. So looking at electricity and concentrating on that, it's clearly going to be a big component of any future power system that we have, any energy system that we have. And we're going to have more and more, as we've seen in a few of the presentations, increase in the amount of electricity that is needed. The only really CO2-free sources are renewables and nuclear. The renewables, wind and solar, we know have issues because they're intermittent, and therefore you've got to have a grid system and a storage system, a delivery system that will actually cope with big changes into intermittency. And that's clearly a thing that changes very much in different parts of the world. The other point we've heard about is that renewables also require a major surface area, which will probably excludes producing as much energy as you would like from them. So I think you're also going to have to use some natural gas as little as possible. But if you do it, you've got to use carbon capture and storage. And that we haven't got organized on a major scale yet. Finally, one remark about electricity: if we do go to big hydrogen markets, which have got to be understood how to do it yet, then of course electrolysis from any excess electricity you have will produce that. The other point I'd like to make is that all of these things have got to fit together into a big grid and distribution system, and that's going to be a major systems challenge for anything that we want to go forward with. Looking at nuclear generation, fission reactors, we've heard about them today quite a lot. They're well developed and they've been operating over 60 years. We know a lot of the issues with them. The great virtue, of course, is that they operate continuously, and that's going to be of great value in any system that we have to develop to deliver energy around. We also know that they're very safe, and we heard lots of descriptions of that. But of course, when we have accidents, that gives people concerns, the public concerns. So the big problem to deal with, and we heard very eloquent presentations today, is the issue of public acceptance with anything that's got nuclear in the title, and particular nuclear fission. And that's going to require continuous communication, just as we heard had happened in Taiwan and continues to happen there. But the other important thing is
1 minute to go.
people have got to have confidence in what is going on. And that means you have to have good, reliable, independent regulation, so that people that are concerned to make these things happen, the reactors happen, don't forget they have details of safety to concern themselves with. The last was the dying to mention was the talk of Ian Chapman. Fusion offers a wonderful opportunity. It gives us an unlimited supply of energy, But I want to emphasize we're a long way off getting to that point, bringing them into the fission reactors as well. Ian was very eloquent about the route to follow forward, but it is still in an R&D, although moving into a deployment phase. Tritium, which doesn't exist and we will have to make, is very valuable. It takes a lot to make that tritium, and it's got a lifetime of 12 years, so you don't have it hanging around because you lose it. So you have to make that tritium in the very reactor that's also producing you the energy. The other thing is that neutron fluxes are enormous, as he again said, particularly leading to potential material damages and potential activation. So a lot of work goes into making sure that you don't activate any of the materials, so you don't have any long-term, long lifetime waste for disposal at the end of these things, but you do have to deal with enormous damage that's caused to the materials that are the absorbers and also contain the lithium from which you make the tritium. And you also here have a safe and almost continuous operation. So it fits the bill very much as fission would, and it has got this enormous supply of energy, far beyond anything that many millennia of generations would require. But this again, I want to emphasize, requires continuous public communication. They have to become familiar with it and feel safe with it. And it also, of course, has to move to having very good independent regulation. Again, the same as in the fission area. So for me, a lot of work has still got to go into the business of making fission reactors and fusion reactors acceptable to the population at large, as well as always being safe. Fortunately, in Britain, we have a society that believes basically in fission reactors, and therefore there is more than 50% of people are interested in having them and recognize how central they are to the energy future. I think I'll stop there. But just to add, nuclear generation provides you continuous CO2-free electricity in any system, and that must be valuable for you to be able to run the complicated systems we'll have. But it does require first-rate independent regulation and public acceptance. Thank you.
Okay, thank you very much, Dr. Cashmore. So next is Professor Cho already there?
Yeah, okay. Thank you, Professor Lee. I'm Hyungyu Cho at Seoul National University, and I was asked by an organizer to introduce microreactor in this panel discussion as one of innovation of nuclear power. So my talk is about the status and perspective of micronuclear reactor. And microreactor is a very small reactor of which power is 1 to 20 megawatts thermal. And I think it can give a versatility to nuclear power and can be a part of future nuclear energy. So let me start from what triggered the research and development of microreactor. In 2018, crusty test was successfully completed. It was a test reactor of kilopower, which is a space reactor developed by NASA and Los Alamos National Laboratory. NASA wants to install 4 or 5 kilopower reactors on the Moon and Mars to provide electricity to human outposts. And crusty was a full power fission test of kilopower, and it demonstrated the performance of the heat pipe and Stirling engine. This great success of crusty test put a spotlight on microreactors. And this slide shows the microreactors under development in the US. And the key features of microreactors are listed here. Factory fabricated, transportable, and self-adjustable, so that the installation time and the number of operators can be minimized. And national laboratories in the US and some startup companies are developing these reactors for special purposes such as space, defense, and remote community, etc. In Korea, R&D on microreactor was recently started. At Seoul National University, we are interested in marine application of the microreactor as Korea has strong shipbuilding industry. We are devising a reactor with a new concept and conducting some experiments on using a rolling platform. KAIST has proposed a hybrid microreactor concept coupling with renewable energy and energy storage. Carrie is designing their own space reactor that has a thermal spectrum for the future. And this slide describes the safety of a heat pipe cooled microreactors. It has much smaller power density and it does not use any pressurized system. Inherent reactivity control is possible with a negative feedback coefficient, and decay heat can be removed by heat pipes and air cooling fully passively without any active devices. So with these features, I believe the microreactor can meet the high safety standard of these days. And these are example applications of these microreactors. I think we have large opportunities in marine applications and inland, remote community, automated mines, data center, EV charging stations can be good applications. Of course, there are many challenges ahead of realization of this reactor. The safety concept needs to be validated for long-term operation. And safeguard and security can become more important issues. And therefore, at the beginning, it should be deployed into only a fully secured and controlled area. In terms of economics, it cannot beat the economics of large LWRs. So it is desired to start the application for special purposes where the cost is not the primary concern. I think this small reactor can give versatility to nuclear power and has sufficient potential to fulfill a mission beyond electricity generation. So I hope this small reactor can become a part of our future nuclear energy in next decade. Okay, this is what I want to talk today, and thank you for your attention.
Great, thanks. So the last one will be Professor Liao. Can you give a very brief introduction of yourself? So please, Professor Liao.
I graduated from MIT and at the same year as Professor Min Lee. And so I have 40 years work experience in Aina, Taiwan. My major is on the thermal hydraulics and two-phase flow. Okay. My talk is that was Fukushima accident preventable with its original design? And this is an important question that everyone who cares about nuclear safety would like to ask. In this talk, I will highlight the importance of improved operational procedure. One lesson learned from Fukushima accident is that improved EOP improvement deserves much more attention. Existing EOP are not adequate enough for prolonged staging blackout because the resources required for performing the EOPs were vastly unavailable and gradually degraded. Therefore, improved EOP need to be developed for Fukushima-like accident. We will demonstrate the Fukushima accident might have been prevented if improved EOP has been used. A real event is used to explain what's wrong with existing EOPs. This is a building on fire, and this is a man waiting for rescue. The alley is too narrow for the ladder cars and the fire trucks to go through, to pass through. The only available ladder is simply not too long enough to reach the person. So the good EOP like this becomes inadequate if lack of resource. Improved EOP may read, try to run down to a safer, which means a lower location before it's too late, and wait for rescue. This is the reactor pressure of Fukushima Daiichi Unit 3. The reactor in danger is at high pressure. The alternative injection can be performed only at low pressure. So you can see lots similarity between these two accidents. Again, improve the EOP will read, try to reach a safer, which means low pressure before it's too late. So we need to do it quickly and properly. To provide alternative in RPV water injection, we need RPV venting. The opening of safety valve in the RPV venting is particularly risky for prolonged SPO because it's equivalent to create an artificial loss of coolant accident. Unlike ECCS, the capability of alternative water injection stent is limited and it's usually designed for low pressure. There is a risk of core meltdown if RPV water makeup is not quick and sufficient enough. Three key factors are involved: RPV inventory loss strain, makeup rate, and duration. Improved EOP is needed for reducing RPV inventory rate. RPV venting is required for the alternative RPV water injection. If we shift the step point of RPV venting from point 1 to point 2, then we can reduce the inventory loss rate from here to here by a factor of 5, significantly reduce the risk of RPV venting. In order to bring the reactor pressure down to point 2, we can open one SRV to perform orderly depressurization while our CIC is available. The risk of reduction of RPV venting and loss has just been discussed. Now let's talk about inventory backup. There are two options available for SPO: RCIC steam-driven or alternate water injection. Different preference will result in different strategy. If more credit is given to the reliability of RCIC, such as in URG, we continuously use RCIC to provide RPV water backup until it is no longer available. To achieve this, we need to maintain the reactor pressure above certain value, for example, the target pressure here, to provide the steam required by RCIC. Once RCIC is no longer available, then emergency depressurization is performed to activate the alternate water injection. This concludes two-step depressurization strategy. If more credit is given to the reliability of alternative native water injections, such as in Fukushima Daiichi, the reactor pressure is reduced continuously to the point where low pressure alternative injection can be initiated. The side effect of this strategy is RCIC will become inoperable. So in both Fukushima Daiichi EOP and URG, controlled pressurization and alternative water in
1 minute to go.
are performed. The only difference is the timing for the activation time of alternative water injection. So the success of preventing core meltdown in Fukushima Daiichi demonstrates the effectiveness of improved EOP. We conclude that Fukushima accident is likely to be preventable if improved EOP has been implemented with its original design. by EOP performed by Fukushima Dai-Ni or by URG. The former one is demonstrated directly. Thank you for your attention.
Thank you very much, Dr. Liao. So let us proceed in our panel discussion. Maybe I throw in the first my point of view. Okay, I have been teaching nuclear engineering for 30 more years, and I always confident that nuclear power is a clean energy, and we are facing the challenging of the climate change. I personally believe that nuclear power is going to play a very important role in the carbon neutralization. And I read on the website here are about 140 small modular reactors, okay, in the design. So I wondering why in the audience, anyone who wants to make some comment about the future role of nuclear power in the carbon neutralization? Any question for the panelists, or there are some you want to express your point of view?
I have some comments.
Sure, go ahead, please.
So far, nuclear power plants were used to generate electricity.
Mm-hmm.
In the future, to achieve carbon-free, clean energy source from nuclear, I think nuclear energy can be used to generate hydrogen as well.
Mm-hmm.
The renewable energy can be used as well through electrolysis to generate hydrogen. But the advantage of using nuclear power plant is that not just electricity, but the heat coming from the steam can be used in the generation of hydrogen. If we use the thermal energy directly, the amount of energy to be used to split hydrogen from water molecule can be reduced. So in the US, using PWRs to generate hydrogen is now on the demonstration stage. And in Korea, that is a very good option. It is more competitive to use nuclear power plant than using wind power or solar power. And with hydrogen, which can be an intermediate measure to have a collaboration between renewable energy and nuclear power. It can be used as a energy storage system. So the load follow can be much easier with the hydrogen generation capability in nuclear power plants. So I think we should consider seriously the option of using nuclear power plants for generation of hydrogen for realizing clean energy future.
Okay, great. Well, we all know that the so-called carbon capture storage going to play a role in the carbon neutralization. Well, I just thought that we can use hydrogen combined with CO2 and synthesize into a fuel. Okay, so we can use the carbon dioxide captured instead of storage. We can use it. So that maybe is a good idea. We can use the nuclear power to generate the hydrogen and use with carbon dioxide we captured and as a fuel. Also, maybe we can design a system that kind of load following, right? If we need electricity, we generate electricity. If we don't need electricity, we use the heat to generate hydrogen. Then use the hydrogen either in the fuel cell or synthesize with the carbon dioxide. Well, I like the idea. So maybe that's a way to use nuclear power effectively.
Can I make a comment?
Sure, please.
On that thing, the one thing I would like to remind people of, and perhaps I went a bit too quickly, but if we're going to get to net zero by 2050, we have to be now starting to deploy some of the final systems that we need. Therefore, I think we need to move as rapidly as possible on even conventional reactors to give us the electricity to supply, to begin the decarbonization, to give us the time to work out all of the sorts of things that you've just been describing, because they were going to take quite a long while to develop, and then you've got to deploy them. And we've got 25 years to do the whole process in, and we haven't got a working example now. The reason why I like to look at electric cars is that we have already hundreds of thousands of them on the road. We've started to understand how they work, what sort of batteries they really need, and things of that sort. You can think of them being deployed and changing all of your car fleet over to electric vehicles, or in that time that you start that, you'll maybe even develop the hydrogen fuel cells to give you your cars. You give yourself the time to do the R and the D on other systems. So it wouldn't surprise me that if we don't have 2 or 3 different energy systems for cars, one on being the hydrogen cells, one the electric batteries in the future. And the same will be true as a mix, because we've always developed better forms of activities as we've had to, but we've had to have the time to develop them and then to get a viable deployment of them. So I think the need for me is, we know we're going to need electricity. We know we're going to need nuclear, a lot of it. The only way of doing that in a grid system is that you've got to have some very stable forms of electricity generation. So you go for them on those grounds. You're not trying to make the arguments for them on other things. You go for that and let these things evolve.
I have a question in my Q&A. What are the main reasons why commercial companies are not investing in microreactors? I don't know which panelists can answer those questions.
Okay.
What are the main reasons why?
Yeah. I'm able to answer the question.
Yes.
Okay. In my slide, I showed some microreactors, the design of the microreactors, and 3 of them are proposed by commercial companies. Like one is Oklor, which is the Silicon Valley startup, and the other one is Holoscan, is also a startup company, and the other one is Westinghouse. So private companies are trying to develop their own microreactors, and they got already some investment already. But in order to realize the reactor and demonstrate the reactor, government support is necessary. So DOE is funding for the demonstration reactor. And in Korea, I met some mid-sized company owner who want to invest for the microreactor, but in Korea, technology is not sufficiently matured. We need to demonstrate the test reactor at first with government support. And after that, if we succeed, and then we can move the private sector. So in the US, private company is already investing, and in Korea, technology is not sufficient for that. Okay, this is my answer.
Okay, I think the next question is also for you. Is district heating an option for cogeneration in Korea?
Microreactor, I think in Korea, grid is fully connected. Even Korea is a small country, so everywhere electricity transmission line is connected. So microreactor is more like useful where the grid line is very difficult to be connected. So for some small island, or some remote area is good for good application for microreactor. And in Korea, for district heat, using microreactor for discrete heating is not a good idea, because already we have some fossil LNG reactor and LNG power plant, and also some combined thermal power plant. So I don't think microreactor is not good. I don't think it is good for district heating in Korea, but good for some small island. Those islands are disconnected from main grid line. Okay, that is my answer.
Okay, Professor, Dr. Cashmere, please.
Yeah. Can I make a comment about the cogeneration? I mean, the thing that you always note about reactors, fission reactors, is that actually you only turn, even the best of them, about 35% of the energy into electricity. You waste 60%. That waste is often in comparatively low temperature heat, because you've done a lot of cooling. And therefore there is I think, scope for doing cogeneration, but it means to say you need to place your reactors closer, I think, to what is going to use that co-generated heat, which then in Britain, for instance, we've put all of our reactors round the edges of the island, so that in case there was a problem, then local communities wouldn't be affected. If you want to do cogeneration, you tend to need to bring the reactors closer to the community that's going to use, for instance, use them for district heating. So, or closer to other industries that you might want to use the heat in. So you have different regulation, I think, problems and licensing problems to make sure that you don't have difficult and dangerous impacts. But I think there's a scope there for using that. But it falls into my category of we don't have really working examples of it that we have at the moment. So you've got to give yourself the time to do the development and see if it does make sense.
Okay, great. Any questions from the audience? Well, in the last session, Professor Ye talking about in Taiwan, we have a public referendum, and the slogan of the referendum is "Go Green with Nuclear." So someone asks us, okay, what the mean by green? Are you referring to using nuclear power to develop, using the time we have nuclear power, and then we can develop renewable energy. We can develop the green energy. Well, my point of view about that is not, because nuclear power is really friendly to ecology. Okay, we saw in the MIT's presentation. Well, it's use the least material to build a nuclear power plant, and its footprint is also the smallest among all the powers. So to us, so-called go green with nuclear, that means we can use nuclear makes the world greener. Okay, that's my point of view about the nuclear.
May I add, Professor Lee?
Sure, go ahead.
In Britain, for quite a long while ago, I knew people that were very, very avid members of Greenpeace, and they, in fact, were anti, to begin with, nuclear power stations for lots of, I suppose, historical reasons. But actually, they all came to understand that nuclear did not produce any CO2, for instance, and so didn't lead you to any climate change, and in that sense was a much greener activity. And they became quite strong advocates of the of nuclear power. And I remember one of them, a man named Monbiot, particularly being forthright at the time of the Fukushima accident, that actually you needed the nuclear reactors to be able to make, as you have just said, a much greener world, a CO2 less world.
Okay, I saw Professor Narabayashi join us. So do you have any comment?
Yes. Today, I have the interview of the NHK television. The difference between the fossil power plant and the nuclear power plant is the nuclear power plant has a fission product in the core. Fossil plant no fission product. And I at the interview, Japanese nuclear power plant has already installed a filtered containment venting system. So if the accident occurs, no more fission product released to the atmosphere. So, and now we are joining the national project to enhance the safety for the filtered content venting system. The system capture even the xenon. The new silver xeroid can have the ability of the capture of the xenon 10 times powerful than the charcoal. So the nothing from out of the containment vessel to the atmosphere, the fission product. This is a national project. It lasts 4 years. We are developing the newest filtered content venting system. This is a revolutionary safety measure to the nuclear power plant. This is my comment.
Great, thanks. Professor Kibiki, do you have any comment?
Actually, I found one question from the Q&A. So
okay,
probably you just go ahead for that.
Currently, there are a lot of resistance to the use of fission reactors. People have no confidence in their long-term safety, as well as the reliability for the storage and the disposal of radioactive waste. Is it still realistic to bet on the revival of fission reactors? Anyone who wants to make comment on those questions? Say, probably you say that probably it doesn't work for us to spend this much effort on the fission power because people do not like it anyway.
But
anyone want to comment on it?
I've let Professor Yu speak.
I think Terence Chen, he did not listen to my talk. The risk of nuclear power has been exaggerated. There has been only 43 fatalities due to nuclear accident. So the life safety has proven by the long operation history of nuclear power. So I think people's perception should be changed. Nuclear power is sufficiently safe enough. And regarding the disposal of spent nuclear fuel, the current technology is able to safely manage the nuclear spent fuels. The short-lived ones, like fission product, they need to be thoroughly managed only for 300 years. The anti-nuke people claims that TRUs should be managed for 100,000 years, but there's no need to carefully manage TRUs for such long period because the solubility of TRUs is so low under the deep underground environment where the oxygens are very little. So if we know the truth about the safety.
3 minutes to go.
Yeah. So if people realize the fact about the nuclear power, I think they will in favor of nuclear power.
I do agree with you. because in our experience, okay, the reason people are against nuclear power because there are so many false news floating around. So as a nuclear professional, we have the responsibility to make things clear. We want people listen to us. I think one of the experience we have from the public referendum, because it is a referendum, so people will think about it. People will listen to trying to figure out which news is correct, which news is not. Okay, so for the public referendum, so I think people will think kind of seriously about it. So we have a chance to make things clear. So what we should do is trying to fight all the false news. Professor
No.
Cashmore?
Perhaps I can also add that I think part of the difficulty is in costs. And people in costs seem to think that you get lots of solar electricity and wind electricity very cheaply, and it's clear you do. But what they don't add into that discussion is the extra costs that you need to build a storage and a grid system that can cope with that. And so often nuclear costs, this is true in Britain, get put in a comparatively bad light compared with these very cheap wind and very cheap solar. But of course, people haven't quite appreciated
to go.
footprint that is going to be taken up by all of the solar farms and the wind farms to produce lots more of energy. Or if you don't take a footprint up on land, you put them in the sea, and then the cost of building them, the systems, becomes very large again. So the costs will I think, as one looks at these things, be able to come down and be very competitive with any of the other renewables. So that's, I think, is a factor in what people think as well.
Mm-hmm. Any comments from the audience or from our guest?
If not, we will end the panel
I have one quick
here.
comment.
Sure.
Today's news, United Nations Scientific Committee declared there's a low possibility of the Fukushima area people got the cancer. Everyone in the world afraid of the cancer during soon after the nuclear power plant accident. But actually, United Nations Scientific Committee declared there's very low risk to the Fukushima people to got the cancer. It is very, very important information to the world people, I think. That's my comment. The newest news from the United Nations.
Thank you for the comment, Professor Narabayashi. So it is about the time to close the panel's discussion session. So
okay, great. It's great to have all of you here, and thank you very much. So let me close this panel discussion. Great, it's great to have all of you here, and thank you very much. So let me close this panel discussion.
Thank you.
Thank you.
Thank you.